Welcome to Chapter 1 of the Chiral Phonons series. In this chapter, we'll establish the theoretical foundations of chiral phonons, covering phonon angular momentum, symmetry requirements, group theory analysis, and the connection to Berry phase. This is an advanced topic at the frontier of condensed matter physics. By the end of this chapter, you'll be able to define phonon angular momentum, distinguish between left and right-handed chiral phonons, identify which crystal symmetries permit chirality, apply group theory to determine phonon chirality, understand the Berry phase connection, and calculate PAM from phonon eigenvectors using Python. Chiral phonons were first theoretically predicted in 2015 by Zhang and Niu in their landmark Physical Review Letters paper. They studied monolayer transition metal dichalcogenides, like WSE2, and predicted that certain phonon modes at the K and K' valleys carry angular momentum of plus or minus h-bar per phonon. The first experimental observation came in 2018 when Zhu and colleagues published their results in Science, confirming the theoretical predictions. This established that phonon chirality is locked to valley pseudospin. Why do chiral phonons matter? First, they enable valley phonon coupling in 2D materials, allowing phonon-assisted valley manipulation. Second, they can transport angular momentum without charge, opening pathways for phonon-based spintronics. Third, phonon chirality connects to topological phonon band structures. Fourth, circularly polarized Raman can selectively probe chiral phonons. Finally, they provide potential platforms for quantum information applications. Let's look at the research timeline. In 2015, Zhang and Niu theoretically predicted chiral phonons in TMD monolayers in Physical Review Letters. The landmark experimental observation came in 2018 when Zhu and colleagues published their results in Science, demonstrating chiral phonons in monolayer WSE2 and 3D alpha quartz. This same period saw extended studies on valley phonon coupling mechanisms. 2019 and 2020 explored chiral phonon transport, phonon Hall effects, and connections to topological phonons. From 2021 onwards, we've seen growing applications in valletronics and phonon devices. Now let's define phonon angular momentum, or PAM. For a phonon mode, PAM is the time-averaged angular momentum carried by atomic displacements. The formula is L equals the sum over all atoms of mass mi times the cross product of displacement ui and velocity, u dot I. This captures the rotational motion of atoms in the lattice. We can express PAM more elegantly using complex eigenvectors. For a phonon mode with displacement pattern ui equals the real part of ei times e to the minus I omega t, the time-averaged PAM is given by this formula. Omega over 2 times the sum of m, I times the imaginary part of ei star cross ei, the complex eigenvector, encodes both amplitude and phase of atomic motion. For 2D materials within plane vibrations, the z component of PAM is quantized. Lz equals s times h bar, where s is the phonon winding number taking values 0, plus or minus 1, plus or minus 2, and so on. Modes with s equals plus or minus 1 are the primary chiral phonons we're interested in. Let's compare left-handed and right-handed phonons. Left-handed, or L phonons, have angular momentum plus h-bar, rotate counterclockwise when viewed from positive z, correspond to sigma plus circular polarization, and have eigenvector proportional to 1, I, 0. Right-handed R phonons have the opposite, minus h-bar angular momentum, clockwise rotation, sigma minus polarization, and eigenvector 1, minus I, 0. They are excited by opposite circular polarizations of light. Here's a simple example. Consider a single atom executing circular motion in the xy plane. U of t equals a times cosine omega t, sine omega t, 0. The velocity is omega times minus sine omega t, cosine omega t, 0. Computing the cross product gives L equals m a squared omega in the z direction. This is positive, indicating left-handed chirality. Reversing the rotation direction gives negative angular momentum. It's convenient to work in the circular polarization basis. We define E hat plus equals x hat plus I y hat over root 2, and E hat minus equals x hat minus I y hat over root 2. Any in-plane displacement decomposes as E equals c plus times E hat plus c minus times E hat minus. The PAM then simplifies to omega m over 2 times the difference of the squared magnitudes, c plus squared minus c minus squared. Now for the crucial symmetry requirements. Chiral phonons require broken inversion symmetry. This is fundamental because PAM is a pseudovector that's unchanged under spatial inversion. In centrosymmetric crystals, for every phonon mode with plus Lz at wave vector q, there must be a degenerate mode with minus Lz at the same q, giving 0 net PAM. Therefore, non-centrosymmetric structures are necessary. Examples include TMD monolayers, alpha quartz, and tellurium. Time reversal symmetry is typically preserved in phonon systems. Under time reversal, T goes to minus T, and angular momentum L goes to minus L. This means that if a phonon mode has Lz equals plus h bar at wave vector k, there must be a mode with minus h bar at minus k, which equals k prime. This is the origin of valley-locked chirality. Lz at k equals minus Lz at k prime. Of the 32 crystallographic point groups, 21 are non-centrosymmetric and can support chiral phonons. The most relevant are D3H for TMD monolayers like MoS2 and WSE2, featuring hexagonal symmetry and valley-locked chirality. C3V for Janus TMDs like MoSSC with broken out-of-plane mirror symmetry. And D3 for 3D chiral crystals like alpha quartz and tellurium, which have three-dimensional PAM. Group theory provides a systematic way to determine which phonon modes can carry angular momentum. For a crystal with point group symmetry G, phonon modes at high symmetry points transform according to irreducible representations, or IREPs. Of G, the key insight is that two-dimensional IREPs can accommodate circular polarization and thus carry PAM. For the D3H point group of TMD monolayers, here are the irreducible representations. The one-dimensional IREPs A'1, A'2, A'1, and a double prime 2 have 0 PAM. The two-dimensional IREPs E' and E" are doubly degenerate and can carry angular momentum plus or minus h bar. For monolayer MoS2 at the K point, the E' optical phonon exhibits circular polarization. Group theory also determines selection rules for phonon excitation. The interaction Hamiltonian is H equals E dot P, where E is the electric field and P is the induced polarization. Circularly polarized light transforms as the E' IREP in D3. H this leads to valley chirality locking. At the K valley, sigma plus light excites the left-handed mode with plus h bar, while sigma minus excites the right-handed mode. At K prime, the selection rules are reversed. The Berry phase formalism, widely used in electronic topology, extends to phonon systems. For a phonon band n with eigenvector un at wave vector q, the Berry connection is an of q equals I times the inner product of un with the gradient of un with respect to q. The Berry curvature is the curl of this connection. Omega equals nabla cross A. The phonon Berry curvature connects to PAM through the Kubo formula. For 2D materials, the z component is most relevant. Omega z equals partial ay over partial qx minus partial ax over partial qy at high symmetry points like K. The Berry curvature diverges for degenerate modes. The integrated Berry curvature over a small region yields the phonon winding number. The Chern number is the integral of Berry curvature over the Brillouin zone. Cn equals 1 over 2 pi times the integral of omega z d squared q for non-interacting chiral phonons. The total Chern number is 0 due to time reversal symmetry. However, valley-resolved Chern numbers are non-zero. Ck equals plus 1 and Ck prime equals minus 1. This provides valley-dependent topological protection. To quantify circular polarization, we define the circularity parameter chi. It's the difference of squared magnitudes divided by their sum. Chi equals c plus squared minus c minus squared over c plus squared plus c minus squared. Chi equals plus 1 is perfectly left circularly polarized, chi equals minus 1 is right circular, and chi equals 0 is linear with no chirality. Analogous to optical Stokes parameters, we can define phonon polarization parameters. S0, S1, S2, and S3, built from the eigenvector components Ex, and Ey the circularity is then chi equals S3 divided by the square root of S1 squared plus S2 squared plus S3 squared. This provides a complete description of the phonon polarization state. For a general complex eigenvector, the atomic trajectory traces an ellipse. The ellipticity epsilon is the ratio of minor to major axis, and the orientation angle theta describes the ellipse tilt. For chiral phonons at high symmetry points, epsilon approaches plus or minus 1, meaning circular motion. At generic Q points away from high symmetry, the motion is elliptical with 0 less than absolute epsilon less than 1. Now let's discuss computational implementation. We can calculate PAM from phonon eigenvectors using Python and NumPy. The key function takes 3 inputs: the complex eigenvector array with x, y, z components for each atom, the atomic masses, and the phonon frequency omega. It outputs the z component of PAM in units of h-bar and the circularity parameter chi. The PAM calculation algorithm works as follows. First, input the complex eigenvector for each atom. Second, decompose into circular basis by computing C+ and C- coefficients. Third, calculate the squared magnitudes. Fourth, compute Lz from the difference and chi from the normalized difference. Finally, determine chirality. Positive chi means left-handed, negative means right-handed. Let's apply this to a realistic example, the E' mode of MoS2 at the K point. We use a simplified 3-atom model with molybdenum at the center, nearly stationary, and 2 sulfur atoms executing circular motion in phase. With masses 95.94 and 32.06 atomic mass units, and frequency 12.5 terahertz, we get circularity chi equals 1, indicating strong left-handed chirality. This mode is valley-locked to sigma plus excitation at the K valley. Let's summarize Chapter 1. We covered phonon angular momentum, quantized as Lz equals plus or minus h-bar for chiral modes. Broken inversion symmetry is necessary for non-zero PAM. Two-dimensional irreducible representations in non-centrosymmetric point groups can carry angular momentum. Berry phase and Berry curvature connect to topological phonon properties, and valley-locked chirality arises from time reversal symmetry. In Chapter 2, we'll explore chiral phonons in real materials. We'll study 2D transition metal dichalcogenides like MoS2 and WSE2, examine valley phonon coupling mechanisms, investigate 3D chiral crystals such as alpha quartz and tellurium, and discuss Janus materials with broken mirror symmetry. See you in the next chapter.